Our neighborhood is a cosmic pinball machine. Rock piles as big as cities plow into the planets and leave mystery in their wake.
Everything we see in the solar system, these are our witnesses, and we just have to get them to talk.
If we don't, we could be one of the next victims of a collision in our solar system. Our solar system is more than just 8 planets and over 170 moons revolving around our sun. Lurking in the vast empty space between these giant bodies are smaller bodies, but small is relative. These asteroids and comets that share our neighborhood have been plowing into the planets since the solar system formed. We have mapped the planets, pored over the data, and everywhere we look in our solar system, we find impact scars. The evidence points to one thing. When we gaze up at our seemingly tranquil skies, they are anything but. Our solar system is a dangerous place. Case in point, our nearest celestial companion is a crime scene spattered with evidence of violent impacts from the past. When we look up at the moon in the night sky, it's a reassuring presence. It lights our nights, pulls our ocean's tides, and marks our days with its phases. But the craters on the moon are anything but reassuring. Like the scars on a prizefighter's face, they have a long and violent story to tell us about epic battles in our neighborhood.
The moon really is sort of the ancient textbook from which we can read the history of the solar system.
The moon's textbook lesson began 4.5 billion years ago with its apocalyptic birth. The moon is the byproduct of a catastrophic collision by something that hit us. A planetoid the size of Mars bore down on the molten, still-forming Earth. As the two massive celestial bodies slow danced towards each other, the planetoid approached at an oblique 45-degree angle and at roughly 6 miles per second.
So the collision would have been, relatively speaking, a low-velocity one. However, the energy of the collision is enormous.
It really pulverized the planet. And it splashed out a giant piece of the mantle of the Earth, just right off of the planet.
Time and gravity caused that material to combine into Earth's moon. Generally accepted today, this violent scenario for the moon's birth was first proposed in 1975 by Dr. William Hartmann and Dr. Donald Davis. But what evidence could possibly lead them to this exact reconstruction of such an ancient crash? They started by trying to understand what the moon is made of. Studies of the moon in the 50s and 60s revealed the moon to be not nearly as dense as the Earth.
The moon apparently lacks an iron core the way the Earth has. The Earth has a fairly high density. The Earth is 5 grams per cubic centimeter. Rock is around 3. So we knew the Earth was 5, so it's a mixture of this heavy metal and light rock. But the moon was only about 3, so it looks like the moon is a rocky object.
But though the moon's density differs from the Earth's, it shares Earth's chemical makeup. In particular, the variations of elements known as isotopes that were found on the moon were identical to those on Earth.
Each part of the solar system has its own isotope composition. You look at the moon, it's exactly the same oxygen isotope ratio. So that beautifully fit the idea that the moon material really was part of the Earth material originally.
So, the moon has a similar composition, yet a different density. Hartmann and Davis suggested that this similar yet different scenario resulted from an impactor-Earth collision that gave birth to a moon composed partially of pieces of Earth's mantle.
If you hit the Earth with something big enough, you could blow a lot of the crustal and mantle rocky material off the outer part of the Earth. Here's the nice little iron core in the middle, and here's the rocky part around it. You now hit that, you blow off all this rocky material, big cloud of debris around the Earth, and the moon forms out of that cloud, then you get a moon that looks like what we've actually got today.
A good theory, but what it needed was backup in the form of computer modeling.
When we're trying to describe how the moon formed, we start with an idea. In this case, the idea is that the moon formed from a large collision with the early Earth. Then we build models, in this case computer simulations, that actually describe what happens during such collisions.
A model with Earth's current rotation and the moon's size as constraining factors.
We have to produce an Earth spin from this impact that gives us this 24-hour day.
Feed the data into the model and you peer back in time to a much different Earth, rotating once every 4 hours in the opposite direction, before it's hit with a glancing blow by a slow-moving impactor roughly the size of Mars. When the impactor struck, its angle, size, and speed all conspired to reset the Earth's spin. The fact that it was a slow-speed collision was a lucky break for the Earth.
If the impacting object is coming in at too high a speed, you can actually blow a planet apart.
In this case, the Earth and the impactor blew apart, and the impactor's iron core fell back toward Earth.
The iron core of the impactor would have merged with the iron core of the Earth, so that it would have increased the Earth's core mass somewhat.
This reassembly process left behind a fairly hellish Earth.
The Earth's temperature would have risen to 10,000 to maybe 20,000 degrees in the interior.
The impact filled the planet's atmosphere with thick silicate particles of vaporized rock.
After something like 1,000 years, that silicate atmosphere of the Earth begins to cool and condense.
Despite its cataclysmic beginnings, the Moon-Earth relationship is all about stability. The Moon's orbit and gravitational pull are responsible for maintaining the Earth's tilt within about 1 degree.
Without the Moon, our models predict that that tilt would actually vary from angles as small as 0 degrees all the way over to about 60 degrees. So that you'd have the North Pole almost facing the sun head-on at times.
Those non-impact conditions wouldn't have ruled out life, but it certainly would have made conditions far more challenging. So while spectacularly destructive, the impact that formed the Moon was a lifesaver for Earth. Collisions in our solar system both destroy and shape worlds.
Why do we want to understand impacts? This turns out to have a lot to do with who we are and what our solar system is like. I think it really is an important cosmic question.
Until the 1960s, most scientists believed the craters covering the Moon's surface were the dead cones of ancient volcanoes.
I came into graduate school in 1961. There are still books being published by reasonable, reputable scientists arguing in favor that all of the craters that we see on the Moon are volcanic.
Gene Shoemaker was one of the planetary geologists who'd become convinced that the Moon had been victim of millions of meteorite impacts. His theory had grown out of his study of Earth's impact craters, which are difficult to recognize and rare. But why are there so many craters on the Moon and so few on Earth?
On the Earth, they often get wiped out due to atmosphere, plate tectonics, the things going on here on Earth.
Shoemaker's work established that impact craters have distinct features. These features can be replicated by firing a bullet into sand.
First of all, there's a rim, kind of a bowl-shaped rim. Also, there's this thing called the ejecta blanket. And this is when the meteor hits, it sends out a whole plume of debris, and that forms a blanket around the crater.
Shoemaker cataloged the anatomy of impact craters by studying the craters left over from atomic bomb tests at Nevada's Yucca Flats. As a result of his work, Earth's impact craters seem to come out of hiding. Armed with his understanding of Earth's craters, Shoemaker intended to use the Apollo moon landings to prove that the Moon is covered in impact craters. He trained the Apollo astronauts to take samples that would test his theory.
Make them take their rock hammers out and walk around and actually understand the geology of the Earth so that when they went to the Moon, they'd be able to think a little bit like geologists.
Armed with Shoemaker's training, the Apollo astronauts provided the evidence that scientists, like Shoemaker, needed to prove that the craters on the moon were impact craters, not extinct volcanoes.
The moon is a witness. The Apollo-era astronauts brought back moon rocks, and all these basins seem to be nearly the same age. That is telling us something.
Rock samples from the craters that covered the moon, taken during NASA missions during the 1960s and 1970s, dated most lunar craters to a specific period a long time ago. Could the moon's impact craters be evidence of the chaotic formation of the solar system? The formation of the solar system was a time when wafting dust and debris from exploded stars, supernovas, orbited the sun and began to clump together under the influence of gravity.
You're starting off with very small things, objects the size of maybe particles in cigarette smoke. And somehow you have to get those particles to all come together in a way to build the planets, asteroids, and comets that we see.
Trails of dusty material eventually collected into their own masses, becoming planetesimals, small planet-like objects, and the process of growth just took off from there.
An object the size of a mountain hits another object the size of a mountain and becomes bigger, and from that you go from mountain-sized things to city-sized things, to continent-sized things, to moon-sized things, to the Earth.
The gaseous planets Jupiter and Saturn are the exceptions to this process.
They had to go through a time where they were accreting a large amount of gas directly from the disk from which the planets form. And that's why they're mainly hydrogen and helium, while the rest of the planets seem to be made up of solid materials.
And in the late stages of that, you had the planets more or less in their current form, but still a few of these giant objects floating around the solar system and occasionally hitting the planets. The early solar system was just a very violent and dangerous place. Without these sorts of giant impacts, we wouldn't actually have the terrestrial planets as we see them today.
But the solar system is just over 4.5 billion years old. The planets took about 50 million years to form, and toward the end of that process came the impact that created the moon. But the rocks the astronauts brought back formed even later. The NASA samples dated the impacts to roughly 3.8 to 4.1 billion years ago. Some scientists believe there must have been another swarm of impacts after the solar system formed. This period of intense asteroid impacts on the inner solar system has been dubbed the Late Heavy Bombardment Period.
The planets got the stuffing knocked out of them. The Earth and the Moon and all of the planets were just pummeled with material from space.
According to some scientists, the heavens produced an onslaught of asteroids and meteoroids during this period. For roughly 300 million years, massive bodies wafted through the solar system, orbiting the sun and intersecting the orbits of the inner planets.
So there was a lot of cosmic bullets that were flying around. They were just flying everywhere.
But what caused the bombardment?
There was a spike in impacts that might have been actually triggered by motions of the outer planets out in the outer solar system, sending in a barrage of comets and asteroids into the inner solar system.
Some scientists speculate that there may have been a domino effect that started when Jupiter and Saturn's orbits shifted, causing a tug-of-war between the planets. This gravitational disturbance upset the orbits of a ring of debris called the asteroid belt, found between the inner and outer solar system. This debris then began to intersect the orbits of Mercury, Venus, Earth, and Mars, plus their moons.
This event happened almost a billion years after the solar system formed, so it sort of occurred during the late teenage years.
And the planets and the moon were sweeping up all the debris that was left over from the formation of the solar system.
Fortunately for us, cosmic collisions at a rate matching the Late Heavy Bombardment Period are gone for good in our solar system.
Every time one of these things runs into a planet, you have one less that's whizzing around the solar system. So you can think about, the planets kind of going around and sweeping these things up over billions and billions of years, and there's going to be fewer and fewer of these objects around. Fortunately for us, we've gotten to a place in the solar system history where there's relatively few of these things, and so we can expect to go for a fairly long period of time without getting smacked by one of them.
But we cannot stop watching the skies, because every so often, one planet or another in our solar system does get smacked by a severe impact In 1994, a massive snowball made a beeline for a giant ball of gas and turned the Earth into a stunned eyewitness. Rock samples from the Apollo missions to the moon convinced most scientists of the severity of what is known as the late heavy bombardment period, when our solar system was trashed 4 billion years ago. But even into the 1990s, many still believe the likelihood of a modern impact with a large object was virtually nil. But geologist Gene Shoemaker set out to show that massive collisions in our solar system were not entirely a thing of the past.
There were a lot of jokes about Chicken Little. It really was out there as an idea and the subject of science fiction movies, but to take it seriously, it was a little difficult to do because you've not heard of anyone who died being hit by an asteroid.
But Shoemaker was one of those who took the possibility of an Earth-killing asteroid impact seriously. He hoped the public would recognize the need to search for future unwelcomed guests of Earth. He would need more, but some believed otherwise. Miraculously, in 1993, the heavens gave him all the proof he'd ever need. On the night of March 24th, 1993, Gene Shoemaker, his wife Carolyn, and amateur astronomer David Levy were observing on the Schmidt telescope at the Palomar Observatory in San Diego, California. But it was a cloudy night, not the best for peering into deep space. They were about to give up.
And I'm looking at the sky, and I'm noticing there's some holes in the clouds, and I'm thinking, you know, there are some breaks in the clouds. Maybe we should continue to observe in the hope we might get something.
David was always very enthusiastic, and he would really push the limits as far as the film was concerned.
But Gene Shoemaker was reluctant. Film was expensive, and the night wasn't promising. David Levy wouldn't give up. Levy won out. They took just 2 pairs of films that night. Reviewing them 2 days later, Carolyn Shoemaker knew she had something unusual.
She suddenly sat up in her chair and she said, David, Gene, I don't know what I have here, but it looks like a squashed comet.
None of us knew exactly what we had because it wasn't like anything we had seen before.
Seeking confirmation of their find, Levy immediately called his friend James Scotty, who was observing at Kitt Peak near Tucson, Arizona. Scotty was doubtful of their findings, but agreed to take a look.
I called him back in a couple of hours. I said, are you okay? And he said, the sound you heard is me trying to pick my jaw off the floor. And I said, Jim, do we have a comet? He said, oh yeah, you've got a comet.
A comet is an icy body, sometimes containing a rocky core that orbits the sun.
And we typically now use asteroid as being something that's rocky and a comet as being something that's icy. The problem with that definition is I think we're beginning to realize that many objects in the asteroid belt are actually icy. And depending on where they were born, they either have a lot of water ice because they were far from the sun, or they were formed close to the sun, in which case they're pretty much water-free.
Comets can be hard to predict because their orbits can be of extremely long duration, up to 1 million years to revolve around the sun. Orbital calculations of Shoemaker-Levy 9, as the comet had been dubbed, revealed that it had passed close to Jupiter in July of 1992, and that Jupiter's gravitational forces had broken it into 21 fragments.
Comets can be pretty fragile, and so you would see one fragment here and another fragment there, but you never saw them lined up like this. And so it was a very exciting discovery. It was really a string of pearls.
Very dangerous pearls that calculations revealed to be on a collision course with Jupiter.
This was fantastic news to Gene, who had always wanted to see an impact.
But reactions in the scientific community were decidedly mixed.
I remember the day that it was announced that Shoemaker-Levy 9 was in fact going to hit Jupiter.